All right, welcome to section 2.7, derivatives and rates of change. So derivatives are something we're going to be talking about for most of the entire semester. So it's definitely good to understand what's going on with these things. All right, let's see. So the problem of finding the tangent line to a curve and the problem of finding the velocity of an object both involve finding the same type of limit. So we've done that a couple times already now. So this special type of limit is called a derivative. And we will see that it can be interpreted as a rate of change in any of the natural sciences or engineering. So this is an important statement right here. Derivative, when you hear the word derivative, you're going to think slope of the tangent line to the curve at a specific point. That's very important, all right? Okay, tangents. So if a curve C, so C is just the curve, a line, a parabola, or any type of curve here, has the equation y equals f of x, and we want to find the tangent line to C, to that curve, at a point, and this got cut off, sorry, but this P, or point A, f of A. Then we consider the nearby point Q, x, f of x, where x is not equal to a, and compute the slope of the secant line. So this is what we did before, right? A couple sections ago. M sub pq means the slope between points P and Q. Then we let Q approach P along the curve C by letting x approach A. So we went over that, right? Remember, we keep bringing those points infinitely close together, and that gave us our limit. All right, so if the slope between points P and Q approaches a number m, then we define the tangent T to be the line through P with slope m. This amounts to saying that the tangent line is the limiting position of the secant line PQ as Q approaches P. Again, as those 2 points get infinitely close together, then the difference no longer matters, right? All right, so this is another one. This is a big important right here. Tangent line to the curve y equals f of x at the point P, A, f of A, is the line through P with the slope equal to this. So this is what we're going to do. We're going to take the limit as x approaches A of this function here. All right, so they'll give you some function. You're going to plug in an x and an a and do all this stuff and take the limit as x approaches A, of course, provided this limit exists. Okay, so this is what we're going to do with this stuff. This is how we're going to apply it. So here's an example. Find an equation of the tangent line to the parabola y equals x squared at the point P, 1, 1. Okay, so whenever we have information like this, we want to find the equation for a line, straight line, right? Y equals mx plus b. We need to find the slope first. Well, again, we only have 1 point, so we can't get a second point here and figure out this slope so close to the point, right? So we'll use that equation up above. We're going to say m, your slope, is the limit as x approaches 1, right? Because the x value here is 1, right? Of f of x minus f of 1 over x minus 1. Again, we're choosing a to be 1 because our x value in the point given equals 1. Now again, be careful, make sure that you are using your limit notation correctly. So limit as x approaches 1. Well, we need to figure out what all this is. Well, f of x is that, right? Y and f of x are the same thing. So f of x is x squared minus, so f of 1 means plug a 1 into the x. 1 squared is 1 over x minus 1. Okay, so we have a function. We're taking the limit. We ask ourselves the 2 questions again. Is our function here, so this guy, is this rational or polynomial? Well, of course, this one's rational, but is the a value here in the domain of this fraction? It's not, right? Because if we plug a 1 in there, 1 minus 1 is 0. 0 in the denominator, we cannot have that, right? Okay. So we got to play a game here, right? We got to try to manipulate this function, simplify it in some way. Well, remember, right there, that is a difference of squares, right? And again, make sure, very, 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 very important on the exam, when you write everything out, you've got to show your work. If you don't show your work, you will lose points. So this is x plus 1, x minus 1 over x minus 1. Well, that worked out nicely, right? Those two reduce away. So we get the limit. Oops, don't forget equal signs either, very important. Limit as x approaches 1 of x plus 1. Well, x plus 1 is a polynomial, right? The domain of any polynomial is all real numbers. So we can plug a 1 in. So again, once you plug in, you drop the limit notation. And there we go. The limit is 2. So in other words, and don't forget what we were really finding here was this is the slope of the tangent line on the curve y equals x squared at the point 1, 1. Okay, so we have our slope and we have the point 1, 1. So now we can just simply plug in, right? So here we go. So, and again, you can use y equals mx plus b. You can use the point slope formula. It's up to you. All right. I'm going to do y equals mx plus b here. All right. So I have my slope of 2. So m is 2. This is a coordinate point, right? So x comma y. All right. So 1, 1. So that's a 1. That's a 1. That's a b. Well, there we go. So if we subtract 2, we get b equals -1. And there we go. The equation of this line is y equals 2x minus 1. Okay? And this is what I would expect to see as far as proper work shown to get full credit for a problem like this on the exam. All right? Make sure you do that. Get all those points. Okay? All right, let's see. We sometimes refer to the slope of the tangent line to a curve at a point as the slope of the curve at that point. The idea is if we zoom in far enough towards the point, the curve looks almost like a straight line. All right, so the figure below illustrates this procedure for the curve y equals x squared in example 1. So what they're doing is, so, there's your parabola zoomed in a certain window. You can actually see right there, right? Those are the window numbers there, right? So if you keep zooming in, right, if you make that window smaller and smaller and smaller, and you'll see if you keep doing this, you can see that this curve now really looks closer and closer to a straight line. Okay, so the real life application of that is, look at the floor right now, wherever you are. The floor looks flat, doesn't it? Perfectly flat. Because you're zoomed in, you're looking really, really close to yourself. But, if you zoom out, in other words, if you go to the beach and look out over the horizon, you see the curvature of the earth, right? So the earth is not flat. Sorry, flat earthers out there, but that one's out. So if you look at the horizon on the beach, you'll definitely see curvature. But as you zoom in other words, as you look closer and closer to your feet, the ground looks perfectly flat. Okay? All right, so the more we zoom in, the more the parabola looks like a line. That's what we're talking about here. In other words, the curve becomes almost indistinguishable from its tangent line. There's another expression for the slope of a tangent line that is sometimes easier to use. So this is it right here. So if we let h equal x minus a, then x equals a plus h. In other words, we're just manipulating this to solve for x. Okay? That's all we did. We added a to both sides. So the slope of the secant line PQ is this guy here. So this looks more like that difference quotient we'd been working with before. Let's see. So see below where the case h greater than 0 is illustrated and q is to the right of p. If it happens that h is less than 0, however, q would be to the left of p. In other words, it's still just talking about bringing those 2 points infinitely close together. All right, and this is the big one right here. This is the one you got to know. Notice that as x approaches a, h approaches 0. And so the expression for the slope of the tangent line in definition 1 becomes this. So this equation here, this is the big one. This is the one you're going to use this chapter. So it's extremely important that you hear what I say right now. Very, very important that you're listening to what I say right now for chapter 2, for the chapter 2 exam. You must, absolutely must use this definition to do a derivative. All right, we'll talk about that in the next chapter or next section. But for chapter 2, for the exam, you must use this notation. If you do not use this notation, if you only use the chapter 3 shortcuts, which most of you won't know about until chapter 3, but some of you do know about them now. If you use the chapter 3 shortcuts only to do problems like this, you will not get any credit. You will get 1 out of however many points. Okay? So you must use this notation, the limit of the difference quotient, anytime I ask you to do a derivative for this chapter, for chapter 2. Okay, of course you can use those chapter 3 shortcuts if you know them to check your work in chapter 2, but you must show this process here, and this is what I'm going to show you. So let's do some of this stuff. All right, so find an equation of the tangent line to the parabola y equals 3 over x at the point 3, 1. Okay, so this one's going to take a little bit of work. It's definitely going to exercise your algebra skills. All right, so again, we need to find the slope first, right? We have a point, we need a slope, then we can put it together and create the equation of a line. So here we go. Slope equals the limit as h approaches 0. Again, you must use that limit notation. So we'll do f of a plus h, minus f of a over h. All right. So in this case, a is, remember, a is your x value in the given point. So a is 3. So here we go again. I know this is going to be tedious. The limit as h approaches 0, f of 3 plus h minus f of 3 over h. So we plug and chug, right? So here we go. Again, limit as h approaches 0. F of 3 plus h. Remember your function notation. It means simply replace x with 3 plus h. So we have 3 over 3 plus h minus f of 3 means replace x with 3. Well, that's 3 over 3. I'll write it like this for now, and then we'll simplify. Okay. All right, so we actually know this is going to be a 1, right? 3 over 3 is 1. We want to combine these two fractions here, so to add or subtract fractions, we need a common denominator, right? Well, in this case, if we multiply this by 3 plus h over 3 plus h, then we've got a common denominator, right? 3 plus, that's a 3 over 3 plus h. Okay, so we work our algebra magic here. Again, limit notation, limit as h approaches 0. So we'll have 3, because we're combining we're going to have a common denominator anyway, right? So we'll have 3 minus parentheses 3 plus h, that's important, over 3 plus h, all over h. We're getting there. I know this is a mess, but we'll get there. All right, since this 3 plus h is in the denominator of the numerator, it can actually go down to the denominator of the whole thing, right? So we'll get 3 minus 3. I'm distributing that negative sign, right? Right here. Okay. So 3 minus 3 minus h over 3 plus h times h. All right, well, let's see. 3 minus 3 is 0. Oh, see, I'm just testing you to make sure you're paying attention. Hopefully you were, because I forgot my limit notation. There we go. Okay. All right, now we have negative h divided by 3 plus h times h, which means h divided by h is 1. Okay, so here we go. Limit as h approaches 0, we've got a negative 1 over 3 plus h. Now we take the limit. So we look at this function, right? Ask ourselves the two questions. Is this a polynomial or is it rational? This one's definitely rational. Is 0 in the domain? It sure is, right? If we plug a 0 in, we do not get a 0 in the denominator. So plug in, we get negative 1/3, and there's the slope. In other words, what you just did was you took the derivative of that function at a specific point. Okay, but we'll talk more about derivatives next section. Okay, so again, we have all this, y equals mx plus b, because now we have a slope and we have the point, right? So we can do this. So remember, this is x, y. All right, so we have 1 equals, slope is negative 1/3, x is 3. B is what we're trying to find. 3 over 3 reduces away. So we'll add 1. So B equals 2, it looks like, right? Sounds good to me. All right, and there we go. Y equals negative 1/3 x plus 2. And there you go. That is the equation of the line, of the tangent line to the curve 3 over x at the point 3, 1. Okay? Practice those types of problems. You will see these on the exam. Very important. All right, velocities in general. Suppose an object moves along a straight line according to an equation of motion s equals f of t. I know it got cut off again, but it's f of t. So position, remember s is your position function. Function f that describes the motion is called the position function of the object. In the time interval from t equals a to t equals a plus h, the change in position is f of a plus h minus f of a, right? So very similar to what we just did, right? So that's what they're showing you here. So average velocities, all that. Again, we're just applying what we just did, take the limit of the difference quotient. Now we can apply it to physics, right? And if you remember, if we have the position function s of t, its derivative, you'll find that out, is velocity, right? All right, so again, we have the limit of the difference quotient here. That's how we're going to find those derivatives, the rates of change. This means velocity at time t equals a is equal to the slope of the tangent line at p, okay? So again, when you hear derivative, you're going to think slope, right? That's very important. When you hear the word derivative, you think slope. All right, another example here. All right, suppose that a ball is dropped from the upper observation deck of the CN tower. I don't know what that is, but anyway, 450 meters above the ground. They want to know what's the velocity of the ball after 5 seconds. So same problem we've been running into. We don't have a second time reference here, right? So creating slope is going to be difficult, but we just found out, well, if we use this formula here, take the limit of the difference quotient, we got it. Okay, so what's the velocity of the ball after 5 seconds? So we want to find v of t, all right, which is f of t plus h minus f of t over h. Oh, I messed up again. See, checking to see if you guys are listening. Just kidding, I messed up. Anyway, limit as h approaches 0 of all that. Okay. All right, so now this is a formula we had from before, so we can write this one down. S of t, that's the position function with regards to time of a falling object, is 4.9 t squared. So this is given. It's not something you have to have memorized. I'm giving it to you. All right. Okay, so we're going to use this as this for f of t plus h and f of t in the equation here in the limit. So let's plug that in. So limit as h approaches 0. So f of t plus h means it's going to be 4.9 t plus h squared, right? We're replacing t with t plus h, minus 4.9 t squared all over h. Okay, so you got some work to do here. All right, so limit as h approaches 0. 4.9, remember PEMDAS, right? So parentheses, well, there's nothing we can do inside the parentheses, but we can do exponents, right? So we're going to FOIL the t plus h. So that's t squared plus 2th plus h squared minus 4.9 t squared all over h. I know it's a mess, but notice what's going to happen. We're distributing this 4.9, right? Right? Okay, so we distribute, we get 4 point, I did it again with the limit notation. There we go. So distributing 4.9 t squared plus 9.8 th plus h squared minus 4.9 t squared all over h. Whew. All right, well, notice this, 4.9 t squared, 4.9 t squared, subtract, we get 0, right? All right, then we're going to simplify. We have h over h here, and we have h squared over h here. All right, so that's what we're doing. We're simplifying. So limit as h approaches 0. We've got 9.8t plus h. All right, so we ask ourselves, is this a polynomial or is it rational? This is a polynomial. Is h in the domain? Is 0 in the domain? Yes, it is, because all real numbers are in the domain of any polynomial. So we plug in and get 9.8t. So now you're thinking, well, wait a minute. We have a variable in this derivative, this velocity, right? Well, yes, because we didn't plug any numbers in up here, right? So we've got now this is actually more convenient, because now we have the velocity, in other words, the derivative at any time, right? So we can plug in any time we want, and we've got the velocity as that ball is falling from that tower 450 meters above the ground. All right, in other words, here we go. We're just going to take this 9.8t. So we're going to say we want, we want velocity at time 5. So 9.8 times 5, which is around 49, in this case, meters per second. There we go. Okay? 49 meters per second. That's the velocity of the ball after 5 seconds. Okay. Moving on, part B here. How fast is the ball traveling when it hits the ground, right? Well, we have the position function, right? S of t equals 4.9 t squared. Okay. So we know that the position, remember, S of t is position, so we know that's 450 meters, right? That was given at the beginning of the problem. Okay, we'll divide by 4.9. Square root both sides. Punch that into a calculator, so the time is approximately 9.6 seconds, right? That, in other words, what's happening here is it takes 9.6 seconds for the ball to hit the ground. But the question says, how fast is the ball traveling when it hits the ground? In other words, what's the velocity at 9.6 seconds? Well, we found the velocity function up in part A. So, 9.8 times 9.6 is something around, so approximately 94 meters per second. Okay. And there we go. Okay. So finally, derivatives. Derivatives are one of the biggest concepts in calculus. Again, when you hear the word derivative, you think of the word slope, right? Rate of change. We've seen that the same type of limit arises in finding the slope of a tangent line or the velocity of an object. We just did that a couple times. In fact, limits of this form here, the limit of the difference quotient, arise whenever we calculate a rate of change in any of the sciences or engineering, such as rate of reaction in chemistry or marginal cost in economics. Since this type of limit occurs so widely, it's given a special name and notation. It's called a derivative, right? So again, super, super important right here. The derivative of a function f at a number a, denoted by f prime of a. So this is important notation here. We state this as f prime of a. Okay, f prime of a just means the derivative at a. So f prime of a, the derivative of your function at a, equals the limit as h approaches 0 of the difference quotient. Okay, so again, extremely important that you know this. Very, 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 very important. Okay, all right, so example 4. So we're going to use this definition here. All right, find the derivative of the function f of x equals x squared minus 8x plus 9 at the number a. Okay, in other words, we're going to find f prime of a, and that prime is a little apostrophe. It's not a number 1, okay? It's a little apostrophe. So we follow the formula, right? It's limit as h approaches 0, f of a plus h minus f of a all over h. Okay. All right, so we're going to plug and chug. Here we go. F of a plus h. Know your function notation means plug in a plus h wherever you have an x. So limit as h approaches 0, we'll get a plus h, quantity squared, minus 8, a plus h, plus 9, don't forget that 9 there, minus f of a. So be careful. Minus f of a means you got to use parentheses. If you don't use parentheses, you will lose points, right? So a squared minus 8a plus 9 all over h. All right, so I'm going to leave this up to you as a little exercise. So you've got to FOIL here, distribute the negative here, combine like terms, bunch of work to do. If you do all that proper, and then divide everything by h, right? And you should always be able to divide by h in these types of problems. If you can't divide everything in your numerator by h, you made a calculation error, you got to go back and look at it. Okay, so we get the limit as h approaches 0 of 2a plus h minus 8. All right, so we ask ourselves, is this a polynomial or a rational function? Well, this is a polynomial, so we're allowed to plug in 0. So there we go, 2a minus 8. Again, that is the derivative. This is going to be a general form of the derivative of this function at some x value a. Okay, so very important that you know how to do this stuff. And again, you've got to show your work on the exam. Don't do this on the exam, right? I'm doing that for the interest of time here. You have to show your work. All right, so we define the tangent line to the curve y equals f of x at the point P a f of a to be the line that passes through P and has slope m given by equation 1 or 2, so the limit of the difference quotient. Since by definition 4, this is the same as the derivative f prime of a, we can now say the following. The tangent line to y equals f of x at a f of a is the tangent line through a f of a, whose slope is equal to f prime of a, which is the derivative of the function at the x value a. All right, so if we use the point slope form of the equation of a line, we can write an equation of the tangent line to the curve y equals f of x at the point a f of a like this. Okay, again, this is just showing you kind of a shortcut. In other words, you find the derivative and you plug in the point that's given for x and y, and you find the slope. You find the equation for your tangent line. Okay, So example 5, find an equation of the tangent line to the parabola. Actually, that's the same one from example 4 that we just did, at the point 3, -6. So from example 4, we found that f prime of a is 2a minus 8. Okay, a is an x value, so our x value in this case is 3. So we have f prime of 3. Notice my notation, f prime of 3. It still means plug a 3 in, right? So 2 times 3 is 6 minus 8, which is -2. So there's our slope, right? So let's use this formula up above. So y minus, so f of a is the y value. So minus -6, notice my use of parentheses here, equals f prime of a, which is the slope -2, times x minus, and our a value is 3. Okay? All right. So we've got some distributing to do here, multiplying here. What we're going to do is, oh, and then so we'll add a 6, we'll distribute, so I'm going to kind of skip a few steps. So we've got -2x plus 6 plus, oh wait, minus 6 at the end, my mistake. There we go, because we're subtracting 6 from both sides. There we go, 6 minus 6 is gone. So there's our final answer. So the equation of the tangent line to the parabola, this parabola here at 3, -6 is y equals -2x. Okay? Okay. So rates of change, again, very similar to what we've been doing here. Suppose y is a quantity that depends on another quantity x. Thus, y is a function of x, and we write y equals f of x, right? If x changes from x1 to x2, so just another x value, then the change in x is delta x. You'll see this notation in physics and in your further calculus classes. Delta x is x2 minus x1, in other words, just the change between the two, and the corresponding change in y is delta y, f of x2 minus f of x1. So this becomes the difference quotient, right? Change in y's over change in x. All right, it's called the average rate of change of y with respect to x over the interval from x1 to x2, and can be interpreted as the slope of the secant line PQ. By analogy with velocity, we consider the average rate of change over smaller and smaller intervals by letting x2 approach x1, and therefore letting delta x approach 0. The limit of these average rates of change is called the instantaneous rate of change of y with respect to x at x equals x1, which, as in the case of velocity, is interpreted as the slope of the tangent to the curve y equals f of x at the point p x1 comma f of x1. In other words, this is all just the physics application of what we've been doing. Okay, so they're just saying if we take this limit, as these 2 points, these two x values get infinitely close together, we have the derivative. Okay, so derivative f prime of a is the instantaneous rate of change of y equals f of x with respect to x when x equals a. The connection with the first interpretation is that if we sketch the curve y equals f of x, then the instantaneous rate of change is the slope of the tangent to this curve at the point where x equals a. The same definition of derivative as before. This means that when the derivative is large and therefore the curve is steep, as at the point P in the figure below, the y values change rapidly. When the derivative is small, the curve is relatively flat, right? Smaller slope, and the y values change slowly. In particular, if your position, s equals f of t, is the position function of a particle that moves along a straight line, then f prime of a is the rate of change of the displacement s with respect to the time t. In other words, f prime of a is the velocity at time equals a. So that's important to remember. If you take the derivative of position, you get velocity. The speed of the particle is the absolute value of the velocity. In other words, absolute value of f prime of a. Okay. All right. So we're actually not going to cover this example here. You won't need it for this class. And so that'll be the end of our lecture there. Thank you.